In this video, we're going to look at the concept of electrical current, what it is, and how it's connected to our unit of electricity. This is ultimately getting us ready to talk about circuits and the other electrical properties, but it's useful to get a sense of what electricity is and what are the different carriers of that charge. So, to start us off, let's talk about charge. You may be familiar with the idea of charge from chemistry. Both protons and electrons have charge, electrons being our charge carriers when we talk about electricity. Well, we can quantify that charge using a symbol Q, and we'll see this in some equations later on, and units of coulombs. So when we talk about charge, we'll talk about it in units of coulombs. How much charge it is given a certain number of coulombs. We'll abbreviate that with a capital C. So if we look at the smallest building block of charge, if you will, that is the elementary charge. This is the charge of one electron, but really it's also the charge of one proton. Protons will be positive, electrons will be negative, but they'll have the same magnitude of charge. And that magnitude, the elementary charge, is 1.60 times 10 to the negative 19th coulombs. A very, very tiny amount of coulombs for one single electron, one single proton. And that means we could figure out how many electrons there are in one single coulomb. So if you started with 1 coulomb, well, basically you can just use this as a conversion factor. You know that every one electron will have 1.60 times 10 to the negative 19th coulombs. Coulombs will cancel, we'll end up with number of electrons, and that is 6.25 times 10 to the 18th electrons. So just like it is a really tiny number of coulombs for one single electron, it takes a lot of electrons to make one single coulomb. And for the record, that's the same as the number of protons required for a coulomb. And again, the only difference is electrons will typically describe as a negative charge, and protons will describe as a positive charge. Well, quantifying charge is going to be important for us later on when we talk about force fields. But right now, we're going to be focusing on the motion, the movement, the flow of that charge. To help us out here, so you don't have to memorize this elementary charge, it is in your IB Physics data booklet. It shows up right there. It's the symbol E for elementary charge. It's the one that's in coulombs. So let's talk about what happens if these charges start to go in motion. Well, the rate at which charges move through a conductor is known as the current. That's how we are going to describe the motion of these charges. And really, you can think of it simply as the flow of electrons. So how fast these electrons flow through a wire will tell you what the current is. And just like we see current of like water flowing through a stream, usually we would talk about that of like liters per minute or gallons per hour. You would have a unit saying how much water and a unit of time saying how fast the water is going. Well, our unit for this flow, this current, is going to have the symbol I. You may remember that from a previous experience with electricity. And our unit for current is the ampere, or just a capital A. Sometimes I will describe this just in terms of amps. It's the same thing if you hear amps versus amperes. It's just an abbreviated way of saying that. Well, I described current for a river of like a unit of how much divided by a unit of time. Well, that doesn't seem to be that. That's actually a derived unit there, a unit of amperes. Um, and it's derived from this idea of charge was coulombs and the current was amperes. Well, the current has to be a unit of how much divided by a unit of time. In this case, an ampere is just a coulomb per second. So if we talk about amps, you can think of it essentially as coulombs per second, and it's the same idea. Coulombs per second is going to get kind of clumsy for us to keep talking about in that term, so we're going to pretty much use amps from here on out. But sometimes you will need to know that this relationship exists. So if you were given a question like this, how many electrons flow past a given point in a wire every second when the current is 3 amps? Well, 3 amps, if I was starting with that, my understanding of what an amp is an amp is a coulomb per second. So if I have 3 amps, it's the same thing as saying I have 3 coulombs flowing past for every 1 second. And that's what I'm looking for, is I'm looking for electrons per second. So Now, all I need to answer really is how many electrons are there in the 3 coulombs that flowed through? Well, I can use my elementary charge. I know that one electron, we can just describe it like this, 1 e minus, is 1.60 times 10 to the negative 19th coulombs. That will make it so that coulombs cancel out, and we have, in the end, just electrons per second, which is 1.88 times 10 to the 19th electrons. So it doesn't feel like a useful thing in this case. Like how many electrons are there in this wire with a certain amount of current? But it's useful to be able to describe with some sort of quantifiable object, in this case being the electron, how fast that current is flowing. So something that I've kind of just used as a given here is that the electrons are the ones that are flowing through. You may remember from your chemistry days that one way that sometimes atoms are represented is something like this, where basically you have a tiny nucleus in there, you've got protons and neutrons, and then around the outside we have these electrons. Well, the electrons are the ones that are going to flow rather than the protons or neutrons because the electrons are very easily lost or gained by neighboring atoms. That is pretty easy to remove an electron and take that electron out of the atom and transfer it to the next one. So these electrons are the ones that are going to flow, not the protons and not the neutrons. Those are stuck inside the atom. So if those were flowing, it would require the whole atom to be moving through the wire, and that's not the case. In this case, only the electrons are being transferred from atom to atom. And what this looks like is something called electron drift. So all of our wires are made up of atoms. Usually those are atoms of copper, because copper atoms are very easy to transfer electrons through. That's what makes them a good conductor. And the wire itself is made up of atoms. The atoms aren't moving. The wire isn't like a tube for electrons. Instead, the electrons exist inside those atoms. And if you add a voltage, so create a positive charge on one side and a negative charge on the other side, these electrons are going to start to move away from that negative and start to drift down the wire. And they're transferring from one atom to the next and kind of hopping over. But overall, these electrons are kind of having this migration from one side to the other. We call the rate how fast these are going. They have a little velocity there on average. We're going to call that the drift speed. And we can actually quantify and measure and calculate that, like how fast the electrons are actually traveling through the wire. And the equation to find that is a little weird, so let's go through where it comes from and how we're going to use it. So imagine this being our cross section of a wire. Here we see that there are a bunch of electrons that exist here. We're going to call that N. Those are the free electrons per unit of volume. We have an area here. That's just the area shown as the cross-sectional area. You may be familiar knowing that it's basically just pi r squared. So the cross-section of a circle is usually what we'll see for a wire. And then we have I. I, again, is our current. That's coulombs per second. And then here, you'll see is a length of the wire. But really, that length is described as a distance. Distance is just velocity times time. So if we know how fast the electrons are moving, their velocity, the length that they travel is the time that it takes. And essentially what this is doing is telling us how much of the wire's worth of electrons are traveling past a single point in a given amount of time. So that means over a certain amount of time, we're going to sweep out a certain volume of this wire. This volume is shown here. And the volume can be calculated. That volume is basically just the area of the wire, the cross-sectional area, times this velocity times delta t. And that's the volume base times height of this cylinder. Well, we can take that a step further and say, now, if we know the number of electrons per unit volume, we know how many electrons there are traveling through this wire in that amount of time. Basically, we just take that volume that we had before. So I'm going to duplicate that and bring it down. And we multiply that by n. N will tell you the number of free electrons, or so that will be the number of electrons total that there are inside that volume of wire that flows through in that amount of time. Well, then if I wanted to figure out the total amount of charge that moves through, I can take that number of electrons, NaV delta T, and multiply it by the charge. Charge is represented by Q. This will help me find the total charge. Now, this is kind of a long walk to get to where we need to go. Total charge. Where we need to go is I want to relate this current to the amount of charges and that velocity of the electron. So ultimately, where this is heading is we can calculate that the current, I, is just equal to the total charge divided by time. It's current, amps, is in coulombs per second. Well, the total charge we just found was NaV delta T Q, and that's divided by the time. That's delta T, and that's going to cancel out. So we're left with this equation that the current, I, is equal to NaV Q. Oh, what a messy little thing. So let's talk about what each of those things represent. You do not need to memorize or know exactly where this comes from. You don't want to drive this, but you will have to use this formula. So I is the current. That is measured in amps. N is the number of electrons per cubic meter. You will see that value that's going to be given to you. It depends on the actual element that you are using. So the material will have a given number of electrons. So copper has a certain N value, gold has a different N value, so on. V is this drift speed, is how fast the individual electrons are moving through. Q is the elementary charge. We know that elementary charge is always going to be 1.60 times 10 to the negative 19th coulombs, because we're always going to be dealing with a single electron in this case. And then A is the cross-sectional area. If it's not already given to you as it being like a rectangle wire or something like that, assume that it's going to be a circular wire. So if you know that the wire has a certain radius, you can figure it out using pi r squared. All right, so let's see what this actually means for us. We're going to go through an example here. The hardest part is going to be units. So suppose that the current in a 2.5 millimeter diameter wire is 1.5 amps, and there are 5.0 times 10 to the 26th free electrons per cubic meter. Find the drift velocity. Well, I think the easiest place to start is just to identify what we are given. First, let's look at 1.5 amps. That is my current. Current is represented with an I. So I is 1.5 amps. This value here, 5 times 10 to the 26th free electrons, that is N, free electrons per cubic meter, rather. N, in this case, is 5 times 10 to the 26th. And technically, that's electrons per cubic meter. And then Q is my elementary charge. That's 1.6 times 10 to the negative 19th coulombs. That will always be the case. So looking at what we have I, we have N, we have Q. We're trying to find V, which means we need to know A. We need to know the cross-sectional area. Well, we are given one other value here. We're given the diameter of this wire, but that is not A. A is pi r squared. So we can take pi times the diameter of the wire, but we're going to want this in meters squared. So we're going to take that and convert it to meters, 0.0025 meters. and then divide that diameter by 2 to get the radius, and then square it, we will end up with an area that is equal to 4.9 times 10 to the negative 6th meters squared. All right, so now we have the area as well, and all that's left for us to do is to solve for V. V is I divided by N AQ. In the numbers that were given, I is 1.5, N is 5 times 10 to the 26th, A is 4.9 times 10 to the negative 6th, and Q is the elementary charge, 1.6 times 10 to the negative 19th. And we're left with a velocity that is much smaller than you might expect. 0.0038, that's in meters per second. So that means for this current to happen, 1.5 amps, which for the record is a ton of electrons per second. That's half of what we calculated earlier. We calculated 3 amps was 1.8 times 10 to the 19th electrons per second. Well, this is just half of that. I'm still only getting a drift speed of basically 4 millimeters a second. So if you had super eyes that you could zoom in on the wire and see the individual electrons traveling through, kind of a standard wire, 1.5 amps is a pretty standard current, you would see these electrons only traveling 4 millimeters every second. So that means it would take basically, in this case, like 20 seconds for an electron to make it a full meter down, which is pretty wild. All right, one other example here. This is an old IB question, the classic IB format of giving you a table of data and then having to identify which row is correct. Well, here we have a diagram showing a wire that has been pinched such that the diameter at X is half the diameter at Y. There's a current of I flowing through Y, and the drift velocity of the current at Y is V. Which of the following is true of the current and drift velocity at X? Well, an important piece here is that current doesn't change. So the reason why current doesn't change is that in order for current to flow through here, those amount of charges need to be able to keep going. If that amount of charges flowing through somehow got smaller, you'd have a huge pileup, and that would then slow down the current there. So for the current to truly be I there, the current has to be I flowing through here as well, which means that limits our options pretty substantially right away. A good trick in these IB type questions is to try to get it to 50% chance as easily as quickly as you can. And then you have to try to figure out the rest. But you at least have a 1 out of 2 chance. So let's look at how this might come out from the equation that we just looked at. So this equation here, if I solve that for V, because I'm trying to figure out how drift velocity compares, V, just rearranging it, is just I divided by N AQ. It's what we did in the last situation. And we now know that the radius is going to track with the diameter. Diameter is half, which means that the radius is R divided by 2. And if we think of my equation for area is just pi divided by, or times r over 2 squared, that the radius is squared, that means that my area ends up being the area that it was before divided by 4. And if the area is now 4 times less, if this area is 4 times less because the radius was half and radius is squared, that means that the drift velocity must be 4 times more. So that means that in that pinched section, the electrons actually have to travel faster then. It's kind of like if you imagine taking a garden hose. If you wanted the garden hose to spray farther and faster, you could put your thumb on it to make the gap smaller. Well, the current is the same. It's the same amount of water flowing through the small gap that you made as it was flowing through the full garden hose. It's just now the individual water molecules have to travel faster to make up the difference. Here you can see that half the radius is a quarter of the area because it's squared, which means that the velocity is 4 times that. So from this lecture video, you should be comfortable talking about what current is in terms of amperes, but then also in terms of coulomb, our unit of charge, and then describe this idea of electron drift and be able to calculate the drift speed from the current.